ARPS for the opportunity to show you guys some of the work that we've been developing recently for the Montebello Islands. I'm incredibly interested in this work and I hope that you guys will be too. So I'll give you an overview of what I'll talk about today. I'll go through a history of the islands as a nuclear test site, the nature of the contamination that's present, some of the radiological surveys and hazard assessment that's been performed there, the environmental monitoring at an existing exposure site and the requirements for environmental monitoring, and then creating a defensible sampling plan to support that monitoring as well. So a little history. So from 1952 to 1963 is when the British government did their nuclear testing program. It was at the Montebellos as well as Maralinga and Emu. So looking just at the Montebellos, there was two operations. Operation Hurricane, which was a detonation of a ship, which was the HMS Plym, and that was off the coast of Chamoil Island on the 3rd of October 1952. So this was detonated and destroyed the ship itself, and there were lots of fragments that became radioactive and were dispersed over the local area. So most of these fragments were cleaned up, thankfully. And then there was Operation Mosaic, which occurred in May and June of 1956. So there's two detonations, G1 and G2. They were both tower detonations. G1 was on Chamoil Island. It was a bit of a smaller one at 15 kilotons. And then G2 on Alpha Island was the largest detonation of the whole British nuclear testing program at 98 kilotons. So you can see on the map here where HMS Plym was off the coast of Chamoil, G1 on the northern tip of Chamoil, and then G2 on Alpha Island. So the nature of the contamination, my favorite thing in the world at the moment, plutonium as a radioactive contaminant was released to the environment. So these detonations were full nuclear detonations. So a lot of the plutonium was, you know, for a better word, used up as the explosion occurred, but there was still discrete particles that were fallout products into the local environment. So their persistence in the environment is determined primarily by their half-life. So fission products with shorter half-lives like cesium-137 at around 30 years and plutonium-239 persist with a half-life of over 24,000 years, plus the decay product americium-241 at about 432 years. You know, they're going to be there for a long time, and hence they're still an issue today. So from the 1960s onwards, multiple radiological surveys and investigations into the status of radioactive contamination at the Montebello Islands were conducted. So these surveys looked at activation products in the soils, close-in fallout at ground zero on Chamoil and Alpha, external dose rates on all of the islands, including the minor islands, so Northwest, Bluebell, Hermite, but they were all looked at for external dose rates. And these dose rates were initially used as the basis for protective actions. So in 1983, there were updated measurements taken to monitor the changes occurring in the environment. So the radiation fields had greatly decreased as expected, and there was no longer presented a health risk to casual visitors. So moving into a bit more present day, mind you, still 30 years ago, in 1990, ARL, which is now ARPANSA, did a comprehensive radiological hazard assessment at the islands, and they quantified and assessed the dose assessments for exposure to artificial radionuclides. So this assessment looked at doses to humans only. There was no assessment of the environment done. Thankfully, Matt Johansson and some of his crew are looking at that sort of work now, which is going to be great. I'm looking forward to it. So from this assessment, it was found that the only potential hazard to human health from residual contamination is inhalation of actinides and from some external whole body gamma radiation exposure. There were surface soils and particle sizes studied at the test sites to get the distribution of radionuclides in the size fractions, and also to determine the plutonium and americium ratios. So this was the purpose of the ratios was so that plutonium did not have to be directly measured using alpha spectrometry or anything more powerful than that, and that gamma spectrometry could be used to analyze all of the soils. There was also the determination of an enhancement factor. So this data, in combination with the land use and habits of visitors at the time, was extrapolated to the resuspension of contaminated dust particles. so that we could look at the possible inhalation of these radionuclides. So using this enhancement factor, it was found that Main Beach on Chamoil presents a potential inhalation hazard. So more details on the specifics of this work can be found in Technical Report 96, which can be found on the ARPANSA website. So the recommendations and current protective actions at the Montebello Islands, there were conservative assumptions of the dust loading and habits of visitors used in the 1990 assessment. So the calculated dose levels up to 1 millisievert, so looking at the public dose limit, which is 1 millisievert, it wasn't considered to present undue risk for visits of up to 1 week. For the external gamma radiation exposure, the minimum allowed period of continuous occupancy at the most contaminated site, which was north of Main Beach and Chamoil, was 32 days. So the inhalation hazard will not change appreciably over a period of several hundred years. However, the external exposure to gamma radiation will continue to decrease significantly over tens of years. So in terms of the advice that is currently provided for the public, it's written here in purple. So camping is permitted on these islands, which you've noticed that Alpha and Chamoil are notably absent, up to 100 metres inland of the high water mark, and for no longer than 5 nights. And it's recommended that a site that has been used before is used again. So unfortunately, the public are not always following these rules. There is camping taking place on other islands, and the general use of the area has substantially increased since 1990. So an updated assessment is appropriate in this case. Oh, went too far. Okay, so when we're looking at doing an assessment and environmental monitoring in an existing exposure situation, we'll look at the ARPANSA guidance, which is the existing exposure guide. Again, this can be found on ARPANSA's web page. And in terms of a monitoring program, the following points are mentioned. So a monitoring plan should be established and implemented, that the provision for monitoring to verify long-term effectiveness of actions for areas in which controls are required as well. The establishment of an infrastructure to support the continuing self-help protective actions. So this is particularly important when we look at the Montebellos, providing that advice to the public that they should only spend a certain amount of time in this area, they can only camp in this area, and this is all supported by monitoring practices. And then overall a long-term monitoring program to maintain knowledge of the residual contamination that is going to persist there for 24,000 years. So looking at the goals and objectives for monitoring sites contaminated, particularly with long-lived radionuclides. So these points come from the IAEA draft safety guide for source monitoring, environmental monitoring, and an individual monitoring for protection of the public and the environment, also known as DS 505, which is much easier to say. So what we want to do with our monitoring plan is to provide lots of information so that we can make the appropriate decisions. So the types of information we want, estimating doses to representative persons and other population groups, identifying areas where protective actions or remediation might be appropriate to achieve dose reduction, supporting decisions and improved radiological management based on protection of the environment specifically, identifying areas where more detailed radiation or radionuclide monitoring might be needed to better estimate doses or define source areas. So this is something that the Montes might benefit from. Determining the effectiveness of remediation, detecting changes and evaluating long-term trends in radiological conditions. As we know, the environment is constantly changing in a site like the Montebellos, in the climate that they're in, you know, high winds, moving dust, erosion practices, sandy soil, you know, all those sorts of things are going to cause changes and trends. And finally, for reassurance of the public, because if, you know, we're here for radiation protection, we want to protect the public and give them as much information as possible so they can take the most appropriate self-protective actions. So the best way that we've found to do this recently at ARPANSA is by implementing visual sample plan. So currently it's in development, but we're looking at using this for routine use in the future. So it's a free software tool, which is fantastic, and it supports the development of a defensible sampling plan based on statistical sampling theory. So What we're looking at here is systematic planning, which is based on the scientific method to ensure that the level of effort in planning is sufficient to provide assurance that environmental data collected will be adequate for their intended use. Conceptual site model development. So this is often a diagram, and it shows your contaminant source, release, disposal, fate mechanisms. It can show spatial and temporal patterns of contamination. It can show media that are contaminated or may become contaminated, and it can also help inform exposure scenarios. And then providing representative samples and measurements. So selecting and consistently applying appropriate sample collection, handling, and measurement protocols. So what I'd like to do is walk you through some of the examples of the Montebellos and how this tool can really support these decision-making processes. So what are our sampling goals for the Montebello Islands? So I'm going to look at 3 for this work. So first one is comparison to a reference level. So we'll look at using the public dose limit, 1 millisievert per year. The second is defining the boundaries of contamination. As I said before, environmental conditions will change, the boundaries of contamination may change, and we want to know where they are. And 3, defining changes to the contamination using existing knowledge or existing samples, like we have the ARL 1990 samples that we can use. So first things first, you define your sample areas as part of your conceptual site model. So this is a screenshot from VSP, which uses Google Street Maps and real coordinates like any other GIS program, while enabling the definition of sample areas. So here I've defined alpha in the blue color and tremoyl in orange. And I've also added the ARL 1990 report data points to this conceptual site model. So VSP actually uses very small dots to, because it's a large area, these small dots to identify the sample places. So I've actually replaced those with some larger crosses, so it's easy for you guys to see. But there are actually 15 samples in total placed onto this map. So data entry, how do you actually get your data into VSP? It's actually really simple, which I was very pleased by. It's a simple copy and paste from an Excel spreadsheet. There's no standard format or column arrangement that's required for it. You can choose where you want your data to go. So that helps when you're looking at harmonization. If you have multiple people or multiple labs that are contributing data, they're not always going to be in the same format, but VSP makes it really easy to handle. So once you've entered your data, then you go to your next tab, which is summary statistics, and that provides some basic statistics that will be helpful in planning our sampling goals. So things like your mean and median and your standard deviation, that's going to be pretty integral to how you're going to plan how many samples you'll put and where you'll put them. And then it provides a simple normal distribution test, which will also aid in our planning process. You need to know if your samples are normally distributed or not. You can see here, our samples are not normally distributed, which is what we would expect considering the discrete particle contamination would be highly heterogeneous at these sites. So comparison to a reference level, this is our first sampling goal. So our first, now we know where we sit with our data, we've got our basic statistics there. We can define our derived consideration reference level, DCRL. So what I've got here is an example DCRL only, it's just for demonstration purposes. So what we're looking at here is defining a measurable activity concentration for americium-241 in a soil sample that is directly related to the 1 millisievert per year public dose constraint. So the inputs here are highly conservative. It's based on the annual public dose limit and 100% occupation on the island for that year. So of course, no one's going to be hanging out on tremoyl for a whole year, but for demonstration and to make it easy as possible to understand, this is what I've used for today. So showing here first, this is the first input that you get for VSP when you're doing a basic fixed true average versus fixed threshold sampling plan. So walking through it all from top to bottom, we've got, I cannot assume the data will be normally distributed, as we know from our basic normal distribution test. So we're assuming that the data are not symmetrical. We want to assess for surface soil. So you can choose the different soil types. You can do multiple soil types at once if you'd like to. We want to calculate the number of samples for one analyte at a time. So I could have analysis for americium and plutonium and cesium and strontium, but I can do them all at one time if I would like to. Obviously, for simplicity, we're just doing americium today. So, of course, our design parameters apply to americium. So specifying our null hypothesis. So I want to assume that the site is unacceptable or dirty until proven otherwise. So that means I want at least 95% confidence that I will conclude the site is unacceptable if the true median is at or above our DCRL of 1.08 becquerels per gram of americium-241. So the next point is our false acceptance rate. So I've put in here if the true median is 0.27 becquerels per gram below the action level. Now I've chosen 0.27 because that is 25% of our DCRL. And again, professional judgment comes in, but this is a very basic percentage that I thought would be a good example for this. And then if it is below that action level, then I want no more than a 5% chance of incorrectly accepting the null hypothesis, again, that the site is dirty. So the estimated sampling standard deviation due to sample variation. Now, this is important when it comes to doing your sampling plan, because if you have a highly heterogeneous site, there's going to be a higher standard deviation, which means you're going to need to take more samples to have a higher confidence level of what is actually there. So we have a standard deviation between our samples with the historical ARL 1990 data of 1.2 becquerels per gram. So that's what I've put in there. And the estimated analytical standard deviation due to the method I've put as 0.1 becquerels per gram, because we know that they were using gamma spectrometry measurements, and this is an appropriate magnitude for gamma spectrometry. And we're doing one analysis per sample. Now, I know that seems like a lot of information, but I promise the more you look at it and think about it, the easier it gets. So what we come up to here is that it calculates that we need to take 344 samples to achieve that level of confidence with the action level that we have and the false acceptance rate that we have and the standard deviations that we have. So VSP will add in a 20% buffer for you just to make sure you're all good. And that gives us 413 samples in total, which is quite a load. Once you've done that, you go on to sample placement. There's different ways you can do your sample placement. You can see there's like random in grids, adaptive. I really like systematic grid sampling because I like some, nice control in my grids, and triangular, just like it. It works really well, actually. So once you've got that sorted out, from a random start point, it actually goes down to being 394 samples as it fits it into your defined sample area. So once we hit apply on that, you can see it's put the white and green dots all over the sampling areas. And it actually gives you the X and Y coordinates for all of these sites that you can execute that plan. And it will also give you a chain of custody so that you can give to your lab and be kind to your lab staff. So of course, if you did this sampling plan, you would have absolutely no doubt where your contamination is and where the boundaries have moved. You would know everything. However, 394 samples is a large load and would be incredibly rare that a lab would have the resources to complete that work. So there is actually a financial component to VSP where sampling analysis costs can be factored in, but I won't be going through that part today. So say we don't want to do 394 samples. Let's use the existing samples that we have. So this is defining the boundaries of contamination. So the second goal that we might want to achieve. So in VSP, this is locating a hotspot. So we've got three options. We can define the size of the hotspot that we want to find. We can define the number of samples that we have, or we can define the budget. So we won't be looking at budget, but if we wanted to find a hotspot with a radius of 100 meters, you can see on the map on the right-hand side, we would need 24 samples. So it's included the ARL 1990 samples in there, as those areas are covered, and it's placed the 24 samples in that triangular systematic sampling grid across the rest of the site. So that looks much better than 394 samples, and it's still going to give you good confidence that the largest area you will have that isn't covered is 100 meters. So what if you only have the resources, time, money, people to take only 10 samples? It's getting out to the Monties isn't cheap. So if we only have 10 samples, then that means that the hotspot increases to 307 meter radius. So, professional judgment and that resourcing still comes into play and plays a large part. And the decision as to which would be more appropriate can also be defined by the land use and the risk appetite for your site. So all of those considerations need to be taken into account. It's not just a numbers game, unfortunately. So what if we take those 10 samples that we have the resources to do, but we have other existing knowledge? We know more about the Montebellos than just those existing 1990 samples. So we have defined areas of higher contamination that this is presented on all the signage around the islands as well in the map that inform people, this is a higher contamination area. So using those 10 samples, we can put them into a stratified sampling plan. So this means that we have 3 strata. As you can see, there's 2 pink, which are the higher contamination. So there's one for G1 up in the north, there's Main Beach in the middle, and then there's the unrestricted area of Tremoille, which is the light blue. So what stratified sampling does is it uses the size of the sampling areas and the estimated standard deviation of each strata from your previous measurements to determine the number of samples that will reduce the uncertainty within each strata. So as you can see, that the blue area has an estimated standard deviation of 0.05. Then Main Beach increases to 0.3 and G1 has 0.24. So the stratified sampling has placed 1 sample only in G1, 6 samples in Main Beach, and 3 samples in the rest of the unrestricted Tremoille area. So something like this could be adequate for reference sampling points for a long-term monitoring plan. And it's great to use the knowledge that we already have to inform that. So what if we don't have any resources to do any more sampling though? Can we determine what level of confidence we currently have? So this is where the non-parametric upper tolerance limit comes in. We're using non-parametric instead of parametric because our samples are non-normally distributed. So that's why it's more appropriate. So looking at this, if we used the 15 samples that we currently have and added in to our data analysis tab, we go across to the tests tab and it has the normal distribution tests, which tells you again that our samples are not normally distributed. But then it gives you an achieved confidence. So our achieved confidence is 58.19%. So looking at, 58.19% for, 15 samples as opposed to the 394 that it wanted before, it's not bad, but is that the level of confidence? Is that the risk appetite that is appropriate for the site that you're looking at? So that's where your professional judgment comes in again. So in terms of decision-making uncertainty, as you can see, even using our statistical sampling theory, which provides great evidence and backing to decisions that we can make, there are still gaps that remain. Specifically looking at the Montebellos, we've got the presence of these hot particles resulting from the detonations. So our contamination is highly heterogeneous and it creates a strong spatial dependency between our samples. You can get 2 samples next to each other that can have, a 10 times magnitude difference in their activity because of one hot particle. So essentially we've got increased uncertainty and that's owing to the large range of reported data and our non-normal distribution. Having that normal and non-normal distribution is really important to understand before you start looking at a sampling plan for your monitoring program. So increased sampling utilising our geostatistical analysis to determine our spatial density may address this uncertainty across all of the islands. So the most effective uncertainty management strategy often relies on a weight of evidence approach. So recognising that there may be several sources of information contributing to a decision that must be made, and not all can be combined in a quantitative way. As I've shown you throughout this, the numbers are great and they give you great evidence, but they're not the only, sort of weight that we have. So where data collection is warranted via further sample collection, utilising professional judgment can be extremely effective. If you have a conceptual site model that adequately justifies selection of sampling locations and establishes how the results from the samples will be used to validate or invalidate the site model, then your decision making will be supported. Thank you.